What's up, Special Relativity fam? Have you ever wanted to do something super simple in an unnecessarily complex way? Well, I have, and I did. And unfortunately, the full tutorial is too long for this video, but I'll link the full video at the end for anyone who's interested. Today I'm going to show you how I use Python to make a program to generate Minkowski diagrams for any given beta and starting position. And if you're thinking to yourself, oh no, I don't know how to program, or oh no, I know how to program, but I don't want to, well, you're in luck, because I did all the work for you and you can find the full code here. As we know, Minkowski diagrams, which are also called space-time diagrams, are used to help visualize how time dilation and length contraction occur when an object travels at speeds near the speed of light. Furthermore, they also help to visualize how certain events may be simultaneous in one reference frame, yet different in another, and how they may occur at different positions in space as observed by different reference frames. We have our rest frame axes, which compose a regular Cartesian coordinate system, where x is the position axis and ct is the time axis. Then we have the transformed position axis x prime, and the transformed time axis ct prime. As an object travels at some velocity approaching the speed of light, its own coordinate system undergoes a linear transformation as seen by an observer at rest relative to it. Even though the rest frame sees these axes transformed, from the perspective of the moving frame nothing has changed, and they would see their own axes as appearing like the rest frame, and forming a 90-degree angle as seen here. To begin, we are going to need to download Anaconda Navigator, which can be found at this link here. Once downloaded, you can run the installer and it guides you through the process easily. Next, we need to ensure we have these packages installed: NumPy and Matplotlib. Both of these should come pre-installed with Anaconda, so you won't have to worry about installing them manually. Each of these have documentation that can be found at these links, detailing their built-in functions. NumPy is a powerful library for mathematical operations and performing operations on arrays of numbers. It also contains built-in functions such as trigonometric functions and square roots and Euler's number. PyPlot is a library that will allow us to visually plot different functions in either 2 dimensions or 3 dimensions. The main thing from these libraries I'll be using I show in these basic examples. I'll be using NumPy to create arrays to populate our x-axis with values which we can then operate on. And then we will also be using the built-in mathematical functions in NumPy. You can see with the plot below, I used np.sinx to create a function for y, which I then plotted. This plots a sine function. The plot function takes an array for the x input, and a function or other array for y. We can also change line styles and colors if we desire. AXV line makes a vertical line at some x, and AXH line makes a horizontal line at some y. And I'll use these to show the rest frame axes, as well as grid lines. So let's go over the properties of a Minkowski diagram and what it can show us. Firstly, it shows how the time and space axes are transformed for an object moving at relativistic velocities. Light, since it is massless, travels at the speed of light, obviously, and so forms a 45-degree angle with both the time and space axes. This is a boundary for all massive particles, which can only travel less than the speed of light, no more. We see in the transformed space and time axes for a moving particle in red that they must form angles less than 45 degrees with their respective rest frame axes. It can be used to show how 2 events may occur at the same time or position in one frame, but not in another. Here, events 1 and 3 occur at the same position in the moving frame, but not in the rest frame. 1 and 2 occur at the same time in the moving, but not the rest frame. 3 and 2 occur in the same time in the rest frame, but not the moving frame. We have a value beta, which is equal to the percentage of the speed of light at which the moving frame is traveling. Beta is equal to the tangent of theta, which, as we know from basic trigonometry, is equal to the opposite over adjacent sides to the angle for a right triangle. In other words, is the slope of the line x prime, and likewise, the slope of the line ct prime is the inverse of beta. Using this information, then we can derive 2 equations for ct prime and x prime as functions of x to use in the program, which you see programmed on the right. We also have the calibration hyperbolas, which show how time dilation occurs, showing unit time and unit length marks in the moving frame with respect to the rest frame. Each unit of time in the moving frame is marked by the intersection of these hyperbolas with their world lines. I'll detail deriving these functions in my full tutorial, but the code for these functions is below in the diagram. The first step is importing the NumPy and PyPlot libraries, which I do like so. Then I make a comment block listing all the functions and variables I define and what they're used for. The most important ones are beta, xrange, which I use to set the limits for the axes to display and make the plot square, posx, which is an array holding all the x values which all our functions will be plotted with respect to, and what I derive for ct prime and x prime axes as functions of x. There is also x naught for the starting position. Here I define the calibration hyperbola functions for both the vertical hyperbolas and the horizontal ones. Then I set the scale and size of the figure using the figure, xlim, and ylim functions in pyplot before plotting anything. Next, I plot both the rest frame axes and the transformed axes using the pyplot function and the ct and prime and x prime functions, setting their colors and labels. After that, I use a for loop to add a grid line at each integer x and y value other than 0 with a light gray dotted line. I follow a similar process using a for loop to add the calibration hyperbolas centered at integer x and y values excluding 0. Then I plot posx and negative posx with respect to itself to add the light lines. For the finishing touches, I label both our x and y axes with x and ct, add the title for the figure showing the beta and x naught value used, and add a legend to the upper left showing which of the lines is the transformed position and time axes. When we run this, you'll see in the console in the bottom right is going to kick out some runtime errors, but it's nothing to worry about since the program still runs. This is just because plotting the hyperbolas, it takes some square roots that are non-real. It can be worked around, but I didn't prioritize that. And there we go. In the top left we see our beautiful space-time diagram, which we can save as an image and print or upload or do whatever we want with. Now, this isn't quite as advanced as it could be, but any more would make this video too long. That said, it is definitely a great start to build upon, and refer to when building your programming skills, and it is an excellent way to apply what we've learned in special relativity so far. Once again, if you want to download this code and play with it yourself, or make it better, I've uploaded the code to this pastebin link here. And finally, thank you for watching and I hope you enjoyed the video.